Hi, this is part 5. We have so far covered the basics of how to set up the mathematical equations that govern the dynamics of a system. In looking at the dynamics, we have only looked at translation. We have not looked at rotation or any other manner of modeling the system. We are looking exclusively at movement and translation at that. Doing rotation is not any different. It just requires a different set of coordinates, and it can be equally done. Instead of inertial mass, you will have moment of inertia and so on. It's not that difficult. I don't want to confuse the issue by bringing in multiple methodologies. So we will now start looking at a simple case, an ideal case. Ideal cases are nice because they are shorn of complexities. They are simplified so much that they have no realism left in them. They can only demonstrate the methodology and the model. So let's start by looking at something extremely simple. We will only take inertia and stiffness and leave out the damping. So we'll just take a look at a spring and a mass. We take this system because such a system, the energy is recovered. Such a system has no loss of energy. And of course, consequently, it's not very realistic, but you will find that as a first approximation, when you do modeling, losses can be ignored to get the first level of answers. The complications introduced by losses, typically first derivative, and the inclusion of first derivative always complicates a problem. Why? Because when you are looking at a differential equation, mx double dot, which is what is represented in Newton's laws of motion, when you look at mx double dot, it's a second differential with respect to time. When you include a first differential, it definitely complicates the issue because mx double dot plus kx can be simply solved by assuming a sine wave as a solution. When you look at the equation mx double dot plus kx, you see a simple situation where something, when it is twice differentiated, must produce the negative of itself. That itself gives you the clue to the nature of the solution. That is why in our ideal situation, we take a situation where only one type of derivative, second derivative, acceleration, comes into picture. So the applicable theory, namely during doing the equations of motion and the Lagrangian, have already been dealt with in part 4. So I'm not going to repeat them here. You can look them up anytime you wish. Definition of the problem is very simple. A spring anchored to the ceiling and a mass m hanging from the spring. It's got an external force F acting on it. The nature of F is not specified here. The center of mass of the mass is x equal to 0, which means the static deflection due to the weight mg is already accounted for since you have redefined the origin at the equilibrium position. Positive deflection is downward deflection. This defines the problem completely. So when we apply the free body diagram approach, you have a downward acting force and you have the spring restoring force acting upward and the external force F. So mx double dot is equal to F minus kx. The summation of external force, which is given in Newton's law, is represented by F minus kx here, as can be seen from the diagram. Rearranging the equation, we get the classic equation mx double dot plus kx equal to F. You can see right here that the left-hand side can be driven to 0 if x is sinusoidal or cosinusoidal. Now, if you rearrange the equation, you will get mx double dot plus kx minus f equal to 0. Now, the homogeneous solution to this problem is, of course, arrived at by setting f is equal to 0. And the Lagrangian approach, where the kinetic energy is given by T is equal to 1/2 mv squared, and potential energy is given by energy of the spring due to deflection 1/2 kx squared, gives you the same equation of motion as the free body diagram approach. So going from there and taking into consideration simple boundary conditions at time t equal to 0, x equal to 0, initial velocity is 1, there are no final boundary conditions. So now we are about to solve the equations of motion to get the response of the system, which in this case is displacement of the mass. Now, in solving the differential equation, our objective is to assume a solution and test it against the equation. If the solution works, then we need to determine the unknown constants in the assumed solution. Primarily, differential equations are not solved by any textbook method or any predetermined method. In this case, the solution is to two form. One is the free oscillation, which is obtained by setting the right hand side to 0. And the other is the particular integral, which takes into account the forcing function. In determining the free response, that is no external load, we simply set the right hand side to 0 and rewrite the equation. We assumed x equal to a sine omega t as discussed earlier, and we differentiate it twice, apply it, so we get x of t into minus omega squared plus k over m equal to 0. Since x of t cannot be 0, because if it is, then there is no problem, we assume that minus omega squared is equal to minus k over m, or omega squared is equal to k over m. Omega, the natural frequency of the system, is square root of k over m. Thus the situation is solved. However, the a in a sine omega t still remains to be determined, and that is where the boundary conditions come in handy. In order to apply the boundary condition, we know that at t equal to 0, x equal to 0. So setting x at t equal to 0, we find that it works out because sine omega t goes to 0 when t is 0 and sine 0 is 0. The next is to differentiate the displacement function. You get a omega cos omega t. And that first differential when t is equal to 0 is equal to 1. So cos 0 is 1. So a omega equals 1 and a is equal to 1 over omega. So we get the solution fully defined. X of t we defined as a sine omega t, where omega squared is k over m and a squared is m over k. The response of the system is obviously a sinusoidal. Consequently, it is cyclic. It oscillates in magnitude between 0 and 1. At this point, we have solved the system for homogeneous response only. I'm not taking into account the particular integral for the simple reason we have not defined the external forcing function. So we will get into that detailed solution at a later point in time. If you wish to look it up, you can look it up in, for instance, S.S. Rao, Mechanical Vibrations, 5th edition, or any other book. Even Olster on system theory will do the job. The point one has to remember is a system response. This is the takeaway from this lecture. The system response is defined by two portions. One is the free oscillation of the system. Second is the oscillation resulting from the forcing function. If you stop and think about it, logically it will occur to you that the free response dies out very quickly, whereas the forcing function response will remain as long as the forcing function is active and will die out once the forcing function goes to 0. So we need to look at both short-term and long-term response when evaluating a system. Very often in considering responsive systems, you will find that the free oscillation or the initial response lasts a very short time in comparison with the long duration. So it would not be too much erroneous to say that you can consider the free response initially and then you can consider the forcing function response later. So that is why we have the expressions transient response and steady state response. Transient response is typically initial. Steady state response is when the system settles down to the response of the forcing function. Thank you.